In this video, I will explain the definition of limit of a sequence and some notation related to it. I assume you are already familiar with the definition of limit of a function, and therefore you have seen other similar statements with quantifiers. I will begin with an example. Let's look at the sequence n over n plus 1 with n starting at 0. The first few terms are 0, 1/2, 2/3, 3/4, and so on. We can draw them on a real line. Here is the 0th term, the first term, the second term, the third, and so on. As n increases, these terms get closer and closer to 1, and they end up crowding around 1. If n is very large, the terms are all very close to 1. We say that the limit, as n approaches infinity, of n over n plus 1 is 1. I would like to write a formal definition of this concept. If you're already familiar with the definition of limit of a function as the variable approaches infinity, you can just use the same definition. Change the domain from the reals to the naturals, and that's all. That will be correct. However, I want to get the same definition from a different perspective, using something unique to sequences. What does it mean that the limit as n approaches infinity of a sequence an is a real number L? In this picture, I see that the terms of the sequence get closer and closer to the limit. I want to be more precise than just saying close to L. I will draw a small open interval centered at L. For this interval I drew, I see that the first 3 terms of the sequence are outside, and after that all the other terms are inside. If I take a smaller interval, perhaps instead of missing the first 3, I will miss the first 10 or the first 20, but after that, the rest of the sequence stays inside the open interval. I'm going to say that I want a tail of the sequence to stay inside of the open interval. A tail means all the terms of the sequence after the first few ones. It could be the first 3, the first 20, the first 10,000, or any other number. The point is that after missing a finite number of terms, the rest of the sequence stays inside the open interval. And I want this to be true for all open intervals centered at L. Great, I have a good idea. Now I need to formalize it. First, to construct an open interval centered at L, I need to give its radius. I will call the radius epsilon. And so this is the interval from L minus epsilon to L plus epsilon. Therefore, I want an to be between L minus epsilon and L plus epsilon. Now to the difficult part. I want these inequalities for which values of n? I am tempted to say for every natural number n, but not quite. Remember I said I can miss the first few ones. Instead, I will say that there is a cutoff, n sub 0, and the terms of the sequence will be in the interval, but only starting at n sub 0. Finally, what am I saying about epsilon? I want this to be true for all open intervals centered at L, so for all positive values of epsilon. Then, if I change the interval, if I make epsilon smaller, the cutoff n sub 0 will also change. Perhaps I will miss the first 10 terms instead of the first 3. And there we have it. This is the definition of the limit of a sequence. Here is the same statement again. This is what it means for the sequence an to converge to the real number L. This is the formal rigorous definition, but I do like very much the one-sentence summary with words. A sequence an has limit a real number L when every open interval centered at L contains a tail of the sequence, where a tail means all the elements after the first few ones. This one sentence contains all the same information as the rigorous statement above with 3 quantifiers, but I find it easier to parse and to remember. It helps gain intuition on what's going on, and it gives us a geometric picture. It also ties with one of the most important principles to keep in mind when working with sequences. To determine whether a sequence has a limit or not, it only matters what happens to the tails of the sequence. Changing the first 3 terms, the first 12 terms, or the first 60 terms could never change whether the sequence has a limit or not. Next, a bit of notation. In this situation, we write that the limit as n approaches infinity of the sequence an is the real number L, and there is the implicit convention that n only takes natural values. Alternatively, we may write this as an right arrow L. And we say that the limit of the sequence is L, or that the sequence converges to L, as I wrote above. One more note. When I wrote that an is between L minus epsilon and L plus epsilon, this is equivalent to saying that the distance between L and a sub n is less than epsilon. Perhaps you are more used to using this second version with absolute values instead of the two original inequalities. That is fine, the two expressions are entirely equivalent. To conclude, two more definitions. When we say a sequence is convergent and nothing else, we mean that it has a limit, and the limit must be a number. Convergent is just a way to say the sequence has a limit without saying what the limit is. Otherwise, we say that the sequence is divergent. So a sequence may be convergent, for example the sequence 1 over n, which is convergent to 0, or it may be divergent, and if it is divergent, it may be divergent to infinity, for example the sequence n squared, or to minus infinity, for example the sequence minus n, or it could be divergent on a different way, and for lack of a better term I will call this divergent oscillated. For example, the sequence minus 1 to the n, the first few terms are 1 minus 1, 1 minus 1, 1 minus 1, and so on, is divergent, but it is not divergent to infinity and it is not divergent to minus infinity. I could also write a precise definition of divergent to infinity, but I will leave that as an exercise.